And I'm excited to be doing this topic. I've been wanting to do some more technical Angular content, and I just kind of took the opportunity here to go for it. And it's always been funny to me that the expression change detection is so closely associated with Angular, because this is actually a process that every modern framework kind of goes through. And we'll get into some of the details there. And specifically, I'm focusing on modern change detection because it's actually evolved a lot through the history of Angular. And the algorithms and the approaches that we have today look very different from the kind of early AngularJS days. So some of you may have seen this kind of equation before, right? I said it's a technical talk. We're getting into math here. The UI equals function of state. This is the core concept, the basic idea that underlines modern web frameworks. From React to Angular, Solid, Svelte. These frameworks break applications into two pieces. You have the state, or the data, and you have some transformation function which describes how to draw a UI based on what that state is. So what we're really trying to say in modern web frameworks is that your UI is entirely determined by the state that your application is in. And that's the framework's job, is to help you manage that state and transform it into a UI, keep what's on screen in the browser in sync with that state. As beautiful as that mental model is, right, reality is not nearly as simple. For one, we can't actually build Angular that way. It'd be really slow if we threw away the entire DOM every time you made a state change in your application and recreated like thousands of DOM nodes. That would be incredibly inefficient. And even if we could do that, the DOM is actually itself stateful. So this is like a simple input element. But already you can see there's some things here that aren't really accounted for in the application state. The user's entered text here, and they've selected a part of that text. So you have a cursor position and a selection state. And also the input is focused when you're typing in it. And those are all things that are kind of inherent to the DOM that aren't captured in what we would normally consider the state of your application. So if we destroy that and recreate it, we destroy the input element, we lose all of that. And that makes the user sad. So modern frameworks get a bit more clever here. Instead of recomputing the entire UI from scratch on every state change, we instead attempt to compute what I would call like delta UI, or the change in the UI. And it's much faster and more correct to do that. That's how browsers actually work, right? Is you make a change to the DOM instead of throw it away and recreate it. And different frameworks have different approaches for this. In React, you do write your components as if you are recreating the entire UI. You return kind of a new VDOM template every time. But it's virtual DOM, VDOM. And React is actually going to diff that with the previous VDOM and decide how did the UI change between these two things. And then it knows what update needs to go and be applied in the browser. In Angular, we actually start by computing what I would call delta state, the change in the state of the application. That's the change in the bindings that are in your templates. And from that, we can combine that with the templates to determine what the update to the UI is that we need to apply. So it's really fun sometimes to reduce, thousands and thousands of lines of complex framework code to, single line equations. So that operation of computing the change in state is what we traditionally in Angular have called change detection. And in the AngularJS days, it really did work exactly that way. The digest cycle would run. It would process all of the scopes of all the components in the application, diff the data, and then update the UI based on that. Today, though, change detection has a lot more responsibility. It updates the UI. It also propagates inputs, runs lifecycle hooks, runs reactive effects, runs render effects, and things like that, all while trying to not break the developer's expectations about rendering and how components work, trying not to break this illusion of UI as a function of state. And in fact, change detection has become kind of an anachronistic name for that process. It's a lot more nuanced than the original concept was. And so we've actually kind of stopped calling it change detection amongst ourselves. We refer to it more as synchronization, the process of keeping the UI in sync with the state. Yeah. Yeah, so if you look at kind of more recent Angular commits, they tend to talk about more like updates to synchronization rather than updates to change detection. And it's because I think developers have this mental model that's from kind of past days of Angular that change detection is this big, massive process that like scans the entire application and is, for lack of a better term, inefficient. And that's not really the case for modern change detection, as we'll see. So we're going to approach this in kind of 3 steps. We'll talk about what triggers synchronization, when synchronization runs, because it gets triggered and scheduled and then runs. And then we'll talk about what it's actually doing. So there are 2 ways in Angular that synchronization gets triggered. When the framework thinks something might have affected state, or when it knows that something has affected state. And you might recognize these as being kind of the zone approach and the zoneless approach. So in zones, we're monkey patching browser APIs, so we know when application code runs. And the assumption is, well, application code ran, it may have changed the state. And so we'll run synchronization on a just-in-case basis. And that's how Angular has traditionally worked. And secondly, we have APIs that you call, and you tell Angular, hey, I actually changed state. I set a signal somewhere I called mark for check, or my async pipe called mark for check for me. And in that case, we can know that synchronization needs to run even without Zone.js. And that's how it works in zoneless. So this is the traditional fits on a slide example of how zone works, right? We monkey patch add event listener to add this schedule synchronization operation at the bottom. APIs like mark for check, on the other hand, right? They're setting some property on a component saying, hey, this part of the tree is dirty, it needs to be checked. And now they're actually calling an Angular synchronization scheduler and telling that scheduler, hey, something happened to the application, something happened to this particular component or piece of state, synchronization needs to happen as a result. In both of those cases, synchronization, the change detection process, does not happen immediately. We schedule it, right? When that process gets scheduled is also something that's different across modern frameworks. So we have a few different approaches. It is possible to just run it immediately whenever something changes. And that is how Wiz does a lot of their rendering. And it's how Solid used to work before some of the batching changes that they've been making recently. In practice, that means when you make a state change, like setting a signal, rendering happens kind of following that change, and then you set the next signal, and rendering happens at the same time, immediately following that. And that's why if you see frameworks that are doing this approach, they'll often have some kind of batching API, some way to say, no, actually, I want to make a bunch of state changes together, and then defer rendering until that's complete. So a common way of avoiding those challenges with synchronous rendering, right, of like rendering more often than you need to because you're changing multiple pieces of state at once, is to just delay it somehow, using a microtask, for example. And that's a way to make sure that kind of all of the state that gets changed synchronously happens together. And that approach is pretty common. In fact, almost all the other frameworks out there that are delaying their rendering are using a microtask delay. It's efficient, it's easy to test, and in the majority of cases, it's exactly as fast as you would need it to be. So multiple kind of back-to-back state updates get resolved in a single rendering operation. And Angular with zones worked a little similarly, although we took a slightly different approach. Zone has knowledge of not just one microtask, but all of the microtasks happening in an event. And so we're able to have zone wait for kind of all of the promises to resolve within a click listener, and then run change detection following that. And that ensures even if you're making changes across multiple promises, they all get resolved together. And these microtask approaches do have one weakness, which is bubbling of events. It's rare, but some applications do register event listeners at multiple levels in the DOM. And if you click a button and that generates a click event, that click event will fire not just for that button, but anything above the button that's listening to click. So if you're doing like click tracking or metrics, or you have UIs that are very hierarchical like tree views, sometimes you will have multiple responders to a single input event. So how do you handle that? Can you bring those things together? The strategies that do that I call coalescing strategies, some way of handling multiple events and waiting to render until all of your events are complete. And it's surprisingly tricky to get this right. So generally, we want rendering to be as batched as possible. We want to do as few rendering operations for all of the state changes that you're doing, because that's fast. But we can't just wait forever. We can't say like, oh, let's debounce rendering by 5 seconds, because that would be a terribly slow and not very interactive application. We want the UI to be consistent and responsive. So we don't want to show the user half-rendered UIs or have UI updates lag. And most importantly, we don't want the page to flicker as state is changing. So we kind of talked a little bit about this and decided that the thing we wanted to go for was when you update state, it needs to be on screen by the next time the browser paints. And that prevents the page from flickering while still allowing us to kind of debounce as many events as we can. So one way of doing this is to schedule with a 0-second or 0 millisecond set timeout. That works great in a lot of cases, right? Turns out that browsers will run all the bubbled events before the timers. Fantastic. It's funny, right? Like set timeouts, kind of a meme in Zone.js. And there were some fun interactions there, too. But it turns out that if browsers are stressed, if they're under a lot of heavy rendering load, they're doing animations and stuff, they can actually decide to stop running timers in order to paint, which would break our model, right? It would create flicker because it's possible for the UI to render before the state updates are fully applied. Of course, there is an API for asking the browser, hey, I want to do something before you paint next time, and that's request animation frame. So that would be great if it weren't for the fact that this thing doesn't run in tabs that are in the background. And users open links in new tabs all the time, and we actually want those applications to be rendering so that when the user tabs over to it, they get a complete application and not just a blank screen that suddenly pops into existence. So it'd be really, a second problem with this, in tests, a lot of testing frameworks will mock request animation frame with a 16 millisecond timer. And yeah, right, like every 16 milliseconds is 60 frames per second. But that artificially slows down the tests if we're really relying on that and doing a lot of these in a test. So it really just doesn't meet all of our needs. And what we want is some combination of these APIs, something that has the guarantees of animation frames, but the kind of runs in the background like timeout does. And eventually, we just decided to use both of them together. So we run both, and whichever one finishes first is the one that does synchronization. So we actually came up with this by talking to the Chrome team deeply about like the task APIs that they have and how the rendering pipeline works and what the right guarantees we needed are. So we call this strategy RAF race, racing request animation frame and set timeout. So now we know like what triggers synchronization and how we schedule it. Next, let's talk about what it actually does, right? What are the steps to the algorithm here? So as I mentioned, it has a few responsibilities. It runs effects. It refreshes the view tree, right? All of the views that in the application that might be dirty. And that's DOM updates, that's input propagation, that's lifecycle hooks. And eventually it runs kind of all of the after render hooks using the after render API. And of course, the view tree itself is quite complicated. You have on push components, you have signal changing, things like that. So the first thing to note is we can't actually do all of this stuff in any random order. Every UI, especially component-driven UIs, have a natural hierarchy, and we need to respect the parent-child relationships in that hierarchy. And I'll give you an example of why that is. So here we have kind of a template which just is showing one binding, user.name, and it's guarded by the existence of user. So if user is defined, then we show their name. In Angular, this creates two views. One parent view that contains the conditional, and a child view that exists or not depending on what the parent view decides to do with it. So let's say that user is defined. So we have this text node on screen, and we set it to undefined. What happens, right? Well, if we run the user.name expression first, the application will crash, right? You're trying to read a property name of undefined. We have to run the parent view first, since the child view is not supposed to exist at all if user is undefined, right? The parents are kind of enforcing this invariant and making sure that the child view never sees a value of user that is not defined. And we have to respect that relationship when we're updating bindings. The same thing is true in effects. So an effect can control the existence of a child view or not inside of a component, depending on the value of some data. And so it can enforce invariance and make guarantees about what data that child view will ever see. So we can't check a child view without making sure all the parent effects have run first. And in fact, every reactive framework that has effects gives these same ordering guarantees. So let's talk about how we actually go and check views, right? There are several ways that we keep track of whether a view is dirty or not, whether a view needs to be checked. It can be marked for check through the mark for check API. That's the traditional operation for telling Angular, hey, this view might be on push, but I changed something that affects it, it needs to run. Marking for check is an operation that traditionally involves marking the parents for check as well. So when you call mark for check, you're not just marking yourself as a component, you're marking your parent and its parent and so on up to the root. That's partly because of host bindings. That's partly an algorithmical thing where we needed to reach that view in the traversal operation in order to check it. So if you had on-push parents, we would have to be able to pass through them as well. A view can also be dirty from signals, since we've had signals in Angular, and that's a different kind of dirtiness. It doesn't mark the parents, and if a signal changes, that doesn't mean the signal has a new value, it just means that it might have a new value. For example, it could be behind a computed, which is going to actually derive the same thing. And so the signal flag is more of a, this might be dirty, and we have to check with the signals before running it. And finally, there's a way a view can be dirty that doesn't mean the view itself is dirty. It just means that something in its child tree, something downstream of it is dirty. Something like an effect inside or a child view. And finally, the application itself has a rolled up concept of what needs to be changed. So we can track, like, for example, when you call mark for check, this notification to the scheduler, in addition to scheduling synchronization, is also setting a flag on the application saying, hey, there's some views that got marked for check, so this is what needs to happen. And with that understanding, we can actually look at kind of what the synchronization algorithm is. And it's surprisingly tame, I think, for something as complex as Angular. Basically, we have a loop. And the loop runs saying, hey, while there are things that need to be checked, we're going to go through this process. And there might be some effects at the top level that are dirty. We need to run those. There might be some views that are dirty. We need to check those. So check the view hierarchy. We have this early exit here, or early loop back, I guess, that says, hey, if there are still dirty views, continue. Why that? Well, it turns out inside of a lifecycle hook or something in a component, you can make more state changes. And as a result of making more state changes, you can make something that previously got checked need to be checked again. And there are some ways of doing this that are kind of going to produce your expression change after check there. But with signals, we decided, OK, we actually want to honor that set, right, the signal set, and go back and check that view, even if it was previously checked. And so that's what this kind of continue is doing here. It's saying if we exit the view, the single pass through the tree, and something got made dirty that we previously checked, we're going to go back and make sure we run it again. And if we get all the views clean, then we can do render hooks. So when the algorithm does start visiting the view tree, which is a recursive traversal, we start at the parents, check if the parents need anything, and proceed to the children. We do so in one of two modes. And these modes allow us, they're the part that allows us to trim away the parts of the algorithm that don't need to be visited, the parts of the tree, while still ensuring that everything that needs to be checked is checked. This is why modern change detection kind of scales with the number of things that became dirty, not the size of your whole application. So global mode is the default for zone-based change detection. And this says we check all of the components that are default, and we don't check on-push components unless they're dirty. We also have what we call targeted mode. And in targeted mode, we skip components that are not dirty and only check the views that have been explicitly, something has told Angular, this needs checked. Targeted mode is the default for zoneless change detection. So the trick is that as the algorithm is descending recursively through the view tree, from parent to child to grandchild, it'll switch between targeted and global mode. So when we hit a non-dirty on-push view, right, an on-push view that doesn't need to be checked, the algorithm will switch to targeted mode to check its children. And that means that things inside the children that are like default change detection, not on-push, will still not be checked until we reach something that does need to be, like a component that changed through a signal. And if we reach that component and we see that it needs to be checked, then the algorithm will switch back to global mode for the children, because that component might be propagating state to its children through inputs or services or something like that. So this flip-flopping allows us to kind of prune away the parts of the tree that have nothing dirty in them, but still allow us to visit child components that are hidden behind on-push parents. So it's a bit complex. Let's look at a couple of examples here. Suppose we're building an application and we have a component tree that looks something like this. We have red components. Theirs will be the default change detection. They get checked all the time in zones. And on-push components are the kind of purple pink here. Let's say we start off by calling mark for check on this right-hand side on-push component. Because mark for check marks to the root, we can see the parent also got marked with the C. I'm using that to indicate kind of the mark for check operation. So in a zone-based change detection, we'll start at the root component, and we check it, and we're in global mode. So checking it will clear its mark for check flag, and then change detection will proceed to its child. Right? This on-push component was dirty, so we check it. This on-push component was not dirty, so we never descended there. And we'll continue down to the default change detection component that's a child of the on-push that was dirty. Notice, again, we skipped the left-hand side on-push here. Was never dirty to begin with. So now let's look at what happens when we're updating the same component with signals, and let's look at it from a zoneless perspective. So first of all, we'll say we're changing the same component, but we're changing it through a signal this time. So I'll use a different letter, S, to mark this is dirty through a signal. Notice the parent does not get a signal flag. The parent actually gets tagged with this, like, I contain something that needs checked. So I'll use a exclamation point. It's not dirty by itself, but we know that it has dirty children. Zoneless change detection starts in our targeted mode. So this root component, even though it's default, not on push, it will be skipped, right? It doesn't need to be checked. But because it has this flag that says, I contain something that's dirty, we will actually propagate through the children. And we will end up checking the kind of on-push component that was marked as dirty through signal. Because we found something that actually needed checked in the tree, we will at that point switch to global change detection mode, which means that the child here that's not on push does actually get checked, as well as any children that it might have. We're still skipping the kind of on-push side of the tree that wasn't dirty. So what we're doing here is tree pruning, right? We're navigating through the whole tree of the application and checking those things where we know there's through the dirtiness flags of either mark for check or something inside is dirty, we're able to reach into those subtrees where we do need to do work, but skip over the parts of the trees where we don't need to do work. So hopefully that illustrates kind of the main points of how Angular checks the views in the right order and avoiding kind of descending into parts of the application where we don't need to. There's another interesting part of this equation, which is what is actually getting checked inside of a view, right? Or rather inside of a component. Today, we're tracking dirtiness at the component level. The component is dirty, the component got marked for check, the component got changed through a signal, and we check all of the views within that one component together. And let's look at why we're doing this. So here's an example with two different views, kind of a for loop that's reading an items signal, and then the child views that get created are just showing a text binding of the item. And you'll notice this is not a signal, right? The item loop variable. The only signal that's being read in this component is the one that's being read in the top level view for the for loop. If we wanted to check these child views and keep track of their dirtiness separately, something would have to say, hey, when this thing changes, right, when the items changes, then the individual loop variables might change and propagate that dirtiness down to the child views. We'd probably need to make the loop variable a signal somehow. even without signals, it's clear that our API is not really designed for talking about dirtiness on a per view level. When you call mark for check, you're calling it on a change detector ref. A change detector ref is a reference to a particular view, but Angular has always interpreted this as the component of this view is dirty, not the individual view itself. So you don't have to call mark for check on every row of the for loop. You can just call it at the top level and know that everything underneath will be checked. And that's kind of the theme here. If we want to change the granularity and process views individually, we kind of have to change the rules of how the framework works. There's a lot of components out there that are making assumptions about what gets changed or what gets checked and what doesn't when they call mark for checked, when when change detection reaches them. This is the basic idea behind what we've talked about as signal components in the RFC, that if you have a way to say, hey, Angular, this component plays by different rules, then we can kind of apply different algorithms for synchronization. We can, for example, say, well, you just can't call mark for check in this component. You have to change it to a signal. That means we can kind of check the views individually and not have to worry about someone saying the whole thing is dirty. We can not have lifecycle hooks at all because those things are communicated through signals instead. You don't need after view checked to tell you your view queries are ready when your view queries are themselves signals. And constructs and templates could also behave differently. So inside of a signal component, the loop variable of a for loop could produce a signal for you, probably some computed based on the items that tells you, OK, this thing changed, so the individual child view needs to change. So modern Angular change detection, or what we now call synchronization, is pretty streamlined. And it handles the kind of past and future sides of things. It handles kind of the previous mark for check operation and signal changes. It handles zones, and it handles zoneless. And it does so pretty efficiently. It scales with the number of things that you're actually changing, not the number of components or the size of your application. So thanks for joining me on this little journey of exploration. Hopefully it wasn't too deeply technical and confusing. I'm still trying to figure out, is this the right format for such a talk? So please let me know. And happy to answer any questions. I think we have a Q&A afterwards, right? Yeah. Excellent. Perfect. Cheers.